Hello, this is a little guide on making assembly codes for custom Robo modding. So the first thing we'll do is set up our Dolphin for assembly code modding. Under config and graphics, turn on render to main window, and under interface, turn on enable debugging UI. Then under view, make sure at least code, registers, and breakpoints are enabled. Make this window a bit bigger, open up the game, and open up memory viewer. Okay, so the code that we're going to try to make is a code that decreases the knockback velocity of Acrobat if Feather Legs is also equipped. So let's think about the things that we'll need to do for this code to work. We need to first check if the Robo has Acro and Feather. Then we need to just decrease the knockback velocity. Seems pretty simple. The way that we're going to write this code is with something called code write. Now this lets us write our own assembly code and compile it into a Gecko code that we can insert in Dolphin. And the Gecko code is formatted in a way to insert our custom assembly code at a specified address. So actually, step 0 here is figure out the insertion address. Generally, we need to be pretty particular about what the insertion address is in order to make sure that our code is doing what we want at the correct time. Let's think about what a good time might be. Probably when the data is loaded into the Robo struct, or the player struct rather. So the player struct is a giant chunk of data for each player, which stores a bunch of data: position, health, the part IDs, all the data for the Robo, all the data for the bomb and leg. So the bomb is the thing that we're going to check. So when the knockback velocity for Acrobat gets stored into the player struct, we're going to insert our own code and check first if it's Acrobat and if the legs are Feather, and then decrease the knockback velocity. So this value here is the offset of the bomb data from the base address. So we'll just do it first for the first player. So bomb data is at this offset. And to get the actual address, we'll just add it to the base address of the Robo1 struct. So this address is where the bomb data for the first Robo starts. So we'll open up memory viewer, and it's all zeros right now, but if we enter a battle, then the data gets loaded in, and this is the data for standard bomb. If we go over to the byte map and go to bombs, the knockback velocity is over here. So on the third row of the actual Robo data, or the actual bomb data, and then it's the third half word over. So these are different names of things. This is the start of the actual bomb data. Third half word over is over here. So this is the knockback velocity for the red Robo's equipped bomb. So what we need to do is check when this value gets written to. So this is at 80276 F2C. F2C. There we go. So this is the knockback velocity. So now we'll go over to Dolphin. Get out of that game. And let's make a memory breakpoint. We'll set the address to this address that we just found, and we'll set the condition to write. So now, whenever the game tries to write to this address, Dolphin will pause the execution, and we can take a look at the code. All right, so we've hit this line, STWU R008 R6. So what the hell does this mean? The first part, this 8005FT4, is the address in memory where this code is stored. The STWU is the actual function that the code is performing, and this R08 R6 part is the data that this function is using. So we look at the assembly cheat sheet. Let's look for STWU. So this is store word and update. The update part is not really relevant. So let's just look at store word. Store word stores the value of RA at the memory address RB plus IX. So it takes whatever value is in this first register and it stores it at the address specified by this register plus this value. So if we go look over here, we're storing the value at R0 into R6 plus 8. R0 has this value over here. R6 has this address. We'll take this address and add 8 to it. And oh look, that's the address that we were just searching for. If we look back at Memory Engine, we see 6F2C, 6F2C. So this line is indeed currently writing to the address that we care about. Now let's just make sure that this line doesn't get used for anything else. So I'll add a breakpoint just by clicking next to the address here. Then under breakpoints, disable this memory breakpoint. So it's only going to break when this line gets executed. I'll click play. It got instantly paused. And I'll continue playing it. You can see that values are getting added into the memory viewer. So this line gets used a lot. It gets called every time it's writing stuff into the struct, which is a lot of times because the struct is very big. So what we need to do is make sure that when we're hitting this line, it's only when we're actually writing into this address. So let's look back at our steps, figure out the insertion address. Yeah, we have that now. We're gonna insert at this address where it's storing the knockback velocity. So we'll put that into code right. Now let's delete this breakpoint and re-add this memory breakpoint on the knockback velocity. Yeah, so it paused as I was exiting because it was rewriting all these values to 0. Go back in, let's pause the execution. So the easiest way to make sure that this is writing to the correct value is just check the value at R6, because this updates every time this line gets called, because it's writing to the next like consecutive value. So if we look at R6, the value is this. Put code right down here. So to this address. So what we can do is store this value into another register that's not being used and then compare it to R6. So the easiest way to get a particular value, like any arbitrary value, into a register is first have an empty register. So we're going to use R20. We'll do lis to set the left half of the register, 0x8027. Then or I, R20 to set the right half of the register to 6F24. So the exact functions of these, it's not that important, but basically this is the structure for setting any arbitrary value into a register. The next thing we need to do is compare between R20 and R6 to make sure that R6 has the value that we're writing to, make sure it's the correct value. So we'll go back over to the assembly cheat sheet, and there's some comparison instructions. So the one we want is CMPW, compare word, because it compares directly between two registers. There's other types of compares for if you're comparing between like a constant value, or if you're like doing a logical compare, but what we need is CMPW. So CMPW, and then we just put in the two registers, R20 and R6. Now the way compares work is they set something called the compare register. The details of this, again, aren't really relevant, but basically what it means is that after we do the compare, the game is just sort of holding on to that comparison value, but it's not doing anything with it. What we need to do is then branch in a particular way based on the value of the comparison. What we should do is use a branch not equal. There's different types of branches based on the value of the comparison, equal, greater, less. If we do this branch not equal, then if this comparison returns not equal, then we can skip over other code. So basically we're comparing between R20 and R6. R20 has the value that we care about. R6 might have the value that we care about. If it doesn't, then we execute this branch not equal and skip over all of the code that's modifying Acrobat. And CodeWrite does this very nice thing where we can just use labels to specify the branches. Otherwise, you'd have to like put in a number of bytes for it to know how long to skip. So I'll add something called orig_op. This will be original operation, and we'll branch to this. So for most codes that you write with CodeWrite, you'll need to specify, or you'll need to add the original operation, because this insertion address, what it does is it overwrites the code at this address, and it doesn't re-add it unless you do that manually. In some cases, this is okay if you're trying to like overwrite an operation in particular situations, but in codes like this one, we still need that operation to execute, because if we go back to the code, this code is storing the value into the memory. If we just don't execute this line, then whatever value we're modifying won't actually get stored into the game. So right-click this, copy code line, and we'll put this under original operation. So back to our to-do list. We've pretty much got the insertion address done. Now we need to check if the Robo has Acrobat and Feather. Check if Facro. These lines are just comments if they start with a hash. I'm using it to help me know what I'm doing here. So if we go over to the memory addresses document, under MISC, these slot IDs will tell us which what parts a Robo has. So we'll check the BOM address and see if it has the ID for Facro, or for Acrobat rather. So first, let's see what this value is supposed to be. Go back to part select and go to this memory address. So right now it's 0. Increase this to 1 here. 8. Okay, so this is probably the correct value. Go over to Acrobat. It's 25. So we need to check if this memory address has a value of 25. So the way we'll do this is we'll do a similar thing as we did up here and store this address into R20. Oops. 0x that, or remediate R20, second half. So now, after these two lines execute, R20 will have this address stored into it. And to check what value is here, we'll use LBZ. LBZ loads a byte and then fills any remaining space in the register to 0. So it's loading the byte at the address specified in this register plus this value into this register. So we're going to load the value into R20 at 0 plus R20. The way the code is written is like kind of backwards, but if you just look at it right to left, we're loading the value specified at this address plus this value into this register. Next, we'll do another compare. This time we'll use compare word immediate. Go back to the compares. This compares between a register and a constant value. And since we know that the value should be 25, we can just do compare word immediate R20 0x25. And we can do another branch not equal to the original operation. So again, if the BOM is not Acrobat, then we'll skip over all of the main code. Next, we'll check if Feather, which is just acro. So the leg is at this memory address. Game. Let's modify this. 1, 2, 3. Okay. So then Feather legs over here is at 0B. So we'll do the exact same thing as we just did, but change this address. It should be BABF, and check the value that we're comparing against, which should be B. So now, at this point, we've checked that we're writing to the correct address, the BOM's knockback velocity. We've checked if the BOM is Acrobat. We've checked if the BOM is Feather, or if the legs are Feather. Now we can actually finally modify the value. So let's turn on this breakpoint again and see what the code looks like at the time of this line getting run. So again, we're storing the value at in R0. R0 has this. So the bomb data is like this. Whoops. So the bomb data is like this. The knockback velocity was the third half word over, so it's this value here. So this register actually has two values in it. It has the knockback velocity, which is this 00AA, and it has the knockback angle, 005A. Now we don't want to change the knockback angle. We still want Acrobat to send upwards, but we just want to make it send with less velocity. So we only need to change this first half of the register. There's a couple ways we could do this. We could do another like LIS or I, but the easiest way is to just store a value into a register and subtract it from this. So what we can do is we'll use R21. This register is free right now. Store into R20. But what do we want to store? So if we're subtracting from this, let's look at what the value is right now. Convert it from hex to decimal. So it's at 170. Let's say we try making it 120 maybe. So convert 120 to decimal from decimal to hex is 78. So currently the value is AA. To make it 78, we need to subtract 32. So we'll store 0032. This LIS will just set the left half of the register, R21, sorry. So we'll set the left half of R21 to 0032, and the right half will just be whatever is currently in there, which is all zeros. So now we can subtract. Let's take a look at the subtract function. There's a lot. Okay, so we need to subtract between two registers. This one, here we go. So this sub will subtract RC from RB and store the value into RA. So it's in this order. Let's go over to code write. So we want to store the value back into the same register that that's writing into memory. So if you look at the original function, we're storing the value in R0. So we want the output of this sub to be into R0. Then we're we're subtracting RC from RB. So starting from R0 and subtracting the value in R21 from that. And this should be it. So this is subtracting 00320000 from this value, which will leave us with the knockback angle unchanged and the knockback velocity reduced to 78. The last thing we need to do is reset any registers that we modified to their original value. So this is what the registers look like during normal execution. We modified R20 and R21. These are currently set to 0, so we just need to reset them to 0. And the easiest way to do that is with MR, which is move register. Oh god. There we go, move register. So move register stores the value in RB into RA. So we can just pick any register that has zeros, like R22, and store that into R20 and R21. As much as possible, you should try to reset any registers that you use back to their original state, because the game is expecting them to be a particular way, and if you modify them with your own code, it could very easily crash the game. So, in general, this will involve zeroing them out, but in some cases you might need to reset them to some other value. So just be mindful of what the original value is. So now we have this finished assembly code. We'll click this arrow to convert it into a gecko code. So let's go ahead and add this gecko code to the game now. Properties, gecko codes, new. Paste it in and run the game. Try. Yeah, that's much more modest than vanilla Facro. So this code has a few caveats with the way we've written it. The first is that we're only setting the values for the red Robo. So if I put Facro on the blue Robo and use them both, you'll see that the blue Robo goes way higher because this is unmodified Facro on the blue Robo. It would be possible, very easily possible to modify the values for every Robo, but that would make this code quite a bit longer. That being said, if we do want to actually make this code something that other people can use, then we would want to make that change. And then another thing to note is that these slot IDs that we're using for Feather and Acrobat, they're based on the order of the parts in the parts list. So if the parts ever get rearranged, primarily if like new parts get added before Feather or Acrobat in the parts list, then these IDs would need to be updated in order for the code to work correctly. And then we're also only checking the ground shot's knockback velocity. If I go back into the game and do an Acrobat with the air shot, you'll see that I still go super high because we're only modifying the ground shot's knockback velocity. So that's another thing that would need to be changed before we actually ship this code, basically. But this should still give a pretty good overview of how you can go about writing assembly codes.